Thank you very much for the opportunity to be here and to start building bridges between countries and societies and artists and mathematicians. Thank you, Milena and Martin, for the opportunity. It's very nice to meet you. And what I believe is in this task that the meaning of mixing art and mathematics is to enjoy math with our senses, and that's fantastic. Let me move this backward, and let me start. I'm going to talk about you of an encounter of math and art that starts with some images that I've been producing from 10 years. It's the construction of a walnut. I will do the following. No, I will show you some images. I will talk you about the reaction of people of the images, and then talk you about how the math behind what's the flavor of the math that are behind, and something about the tricks of the visualization and the story of the coincidence. First of all, I will show you this image. I like it very much. It's surprising because it has some, how do you say, brightness and something mysterious behind. But if I told you that there are math inside of this image, or when I told people that there are math hidden in there, several questions appears. If you see this one, you can see it as a sculpture or something that came from the imagination of somebody. But in the next one, you feel that there is a pattern. There's something hidden, and most of the people ask. It's strange because if you talk to people about math, nobody's interested in what the formulas are or what's the operation you are doing. But once you show these images, people really want to know: is there a formula? What are the numbers behind? What I'm supposed to see on that? Not only for the image, but for the math part. I have one of these pictures hanging in my bathroom in my house, and all the visitors always ask me something. No, I want to know what's there. And as I learned, if I make a technical explanation or too much details, as always, are not so welcome. People get bored very fast. And the art part of these images is trying to tell the processes behind of the image, not only on the creation of the image itself, but for the math, that part of the math that's marvelous. When you think about something like this argument of the two segments of a line have the same number of points, that it's really weird, but when you see it, you feel, wow, that's something special. And what I wanted to try to build is that this real object, this math object, has to be constructed in the mind of the viewer. Something weird is that nobody asked about the name. I mean, when you say wild nut, people say like, okay, it's natural because I mean, it's not a frequent question. Well, in this talk, I will told you the recipe to build these wild nuts. And for that, you need, of course, a knot, but a tame knot. Several spheres that are reflecting spheres and a little patience. First of all, I said wild knot, it's something strange. I may use the notion of tame knot. The tame knot, it's the image of a circle embedded in the tree space. I like to think of it if like if you draw a circle in the space, not in the plane, not in your paper. You draw a circle in the space, you obtain a knot in this three dimension. It doesn't have endpoint, doesn't have self-intersection. This is not like the shoelaces. It doesn't have ended, and it has a finite number of crossings. What's a crossing? Is what you see when the knot crosses. When you draw the knot in a plane, you see that some part crosses over or beneath the other part of the knot. This trefoil knot has 3 crosses, and we have a huge catalog of tame knots. Actually, they are infinitely many tame knots that they are cataloged by the number of crossings the draws have. You can see the simplest 250 knots up to, I believe, 6 crosses or something. And you start with the first circle, the circle, the trivial knot, and then the trefoil and 8 figure knot, and etc. There are a lot of them. And actually, they are beautiful. Then you have, then you need for the recipe a sphere mirror. Well, it's a trick. Sphere mirror, as you can see in this beautiful picture of Dali, everything gets distorted. When you see, I don't know if in Germany or Austria you have in Christmas, but in Mexico you used to hang spheres made of glass in the Christmas tree. Very nice. Well, I think nowadays they are plastic and Chinese and terrible, but years ago we have these beautiful crystal spheres, and you can see your face inside, like Dali, and you see like fish face or something. And there is something that does not get distorted. The image of a sphere. If you reflect a sphere, the other spheres of the Christmas tree, they share the same structure. They don't get deformed. But from the mathematical point of view, I'm thinking in the inversions with respect to the sphere. Inversion with respect to the sphere is something that we learned in the, I believe, in the first years of the degree. If you take a circle with center C and a circle S, and you want to compute the image of the inversion of the point P, you draw the tangents, then you draw the line orthogonal to the line between the center and the point, and you get a proper function. And this proper function, called inversion, preserves circles, not in the plane, but on the compactification of the plane, which is the sphere. And then you have a fantastic transformation. And this transformation can be defined also in 3 space. Instead of taking lines, you take the cone, the tangent cone, and compute the same point. So what's the idea of the process? Imagine you have, this is a 2-dimensional picture to get the details. You take several circles. We're going to use, in this case, 7 inversions. And the position of the circle is important. You make it like a necklace where the spheres are tangent to each other 2 by 2. And we want to compute the inversion, for instance, with respect to the green circle. The image of the blue circle, it's another sphere that is tangent. And we can continue this with the rest of the necklace. So we have a small copy of the complement of the others, the non-green spheres inside of the green sphere. And then we can use it in the other spheres. Sorry. In the blue sphere, we have the copy of the complement, and so on, obtaining a new necklace made of smaller spheres and sharing the property that they are tangent to each other, and making a necklace with more spheres and smaller, and inside of this contained in the spheres. So we can repeat the procedure. That's the marvelous of mathematics. When you have something and you know how to build the next step, you can continue to the infinity. Instead of computing the reflections on the larger spheres, we can do it in the smaller one, copying and making it smaller and smaller. You can imagine at the limits of these constructions, once one obtains the image of a circle, a fractal circle. So this is the key. What I do in these images, I take, I don't know, 32 spheres, put it on a necklace, like the grandma necklace of pearls, tie a knot in any, following the diagram of any tame knot. I close it and I observe. You can see this is the threefold knot with, I believe, I don't know how many spheres, like 32 or something. And you can see in the reflection the image of the necklace. But really, in the mathematical construction, we have a copy of the necklace with the structure of the knot. And this procedure repeats to infinity, obtaining a circle what is infinitely knotted, or what is called a wild knot. Okay. If I have time, I will show you a video of 3 minutes that has something also related with random music. But if not, I leave you this link, and I will talk about this later. So what happened in this procedure? What happens in our mind is we started with something, give us a way to construct the next step, and we have this feeling that when you enter in an elevator with 2 mirrors in the walls, that you see the infinity. Obviously you don't see the infinity, but you feel that there is infinity. And that's the same. And this construction happens in a bounded space of your mind. It doesn't go far away like in the elevator. This happens very near. And as I said, in the limit, once one obtains this image of the circle embedded in the tree space. That doesn't happen so often in the viewers. People which are not mathematicians, it's very difficult to understand this huge step that is going to the limit of a construction. But they can imagine that each time you see, even if with a mental microscope of any scale, you can see, they can feel that this structure of the necklace became more and more knotted. Behind of this is the notion of a limit set of the action on S3 of a Kleininan group. You can do all this process not only with necklaces. You can use it in several spheres configuration, and you obtain fantastic images around them. Well, now I can show you again the same picture of the beginning, and you now may, I hope, to understand a little bit more of the mathematics behind. Let me show you the next one, that is fantastic. You can see this repeating process, and I wanted to make this go to infinity in the computer, but it's impossible. The problem is that the number of spheres grows like n square on each iteration, and this 3D Studio Max or these programs that use PovRay get very tired with the number of spheres, because they are very small and they go away from the precision of the machine. But on the other side, we have these PovRay programs that simulate very nice mirrors in different shapes. Okay. All these knots live in the world of ideas, or in the rendering, or in the computer. But in the real life, this is the part of the encounter. Some time ago, I found this image, precisely this image on the internet. A friend hand me to, let's see, there is a French guy that is making necklaces in the Pompidou. And we start a very nice collaboration after that. We wrote a book about this coincidence that two people, two countries, two intentions thinking on the same subject, but with the same and with the same objective. This, I don't know how to say it in English, but point to marvel, that let people enjoy something. For him, the art or his construction, and for me, this mathematical part that amazed me. And in the book, we have I tried to write an article, a paper, or something like a paper, math paper, but in order for the non-mathematician people can feel what is the feeling of a mathematician reading a paper not on, in your area about this construction. It wasn't so successful. I think nobody read it. And but something that drew attention was when I tried to catalog or characterize the notes of the sculpture of Jean Michel, I used the Dr. Tix and White notation to know which notes were, and he got marvelous with the sketches I made for him to know that this is the 5-2 note of the table. Okay, this story converged into a great and very large exhibition that happened in Buenos Aires. I will talk about later, but with his sculptures, or like a catalog of his sculptures, we included the images, the rendered images I produced. This is a 3/4 knot, and it's a very large iteration of this process, and you can see this beauty, this complexity happening inside all the spheres. There's another one, and you can see here in the thinnest part of the image the reproduction of these knots. Jean Michel, and that this is a Jean Michel sculpture that he donated to the Museo of Ciencias at UNAM, called the Lacan knot. You can see both of us in the part of the exhibition dedicated to this construction and this coincidence of this encounter in Imaginario Matemático. As you can see behind this a tame knot in contrast. And happened and make people get interested in this encounter. The strength of the sculptures of Jean Michel is fantastic. The strength of the mathematics behind it's fantastic. But together in this, using this math part and using this art part in the exhibition, draw the attention in a way that it ended in an exhibition in the Centro Cultural Kirchner in Buenos Aires, a very huge place with all the sculptures. And this picture in the low corner, I love it very much, but that's the feeling that somebody I wanted to produce, or I want people enjoy not only the sculptures or the wild notes, math. It's something she represented that amaze part. Sorry. Well, these exhibitions continue in the world, continue with a very high impact. And in the exhibition in Montreal, in the Arsenal Contemporary Art, they wrote this, and I bolded one part of the phrase that this: the interaction of contemporary art and mathematics confers to the exhibition a fertile symbolic terrain. It generates invisible links between the rational and the intuitive. And I wanted to stress that this interaction confers not only to the exhibition, it confers the same fertile symbolic terrain for the math that is very explosive. It draws attention of the people, not only for the art, but for this mental processing that I wanted to share to a lot of people. This nice picture is in Buenos Aires, when we have together the math part and the art part that make this fantastic link. Since you are in Europe, if you go to Paris, go to the Petit Palais up to the January all this year. There is a huge exhibition also of these sculptures. It's close to you. I wanted to go there, but it's complicated to travel in these days. Well, conclusions. Math and art together are much, much stronger. They together are very, very strong. They provide a new layer of meaning in both sides. And that's very, very surprising for me. In the beginning, I believed that, well, I will take a huge, some help from the art, making this possible or making this much more viewable. But on the other side, for the art, it his meaning grow a little bit with the math notions. And the final conclusion is math is beautiful and surprising when you see it and when you're thinking. And as we heard in the previous session, and also is surprising when you hear it. I believe I have 4 minutes. I will show you the video because also not only has the construction of these wild notes, the music is computed randomly by a computer. Let me